So thank you for the invitation, and I'm very pleased to be here. I will do a super brief recap of the morning. So as the talk before, I will be interested mostly in stochastic dynamical systems, mostly because with stochasticity we have a probabilistic structure on top of it, which allows us to do and to have statistical learning theory, as Massimiliano described before me. And so I will be interested in the transfer operator, which is just a conditional expectation operator over a family of observables. And really, when we started this interest in learning dynamical system, the first question that we asked ourselves is, how do we learn a dynamical system? What does it even mean? And then we basically came up to the fact that for a very general class of stochastic dynamical system and Markov processes, this transfer operator is a well-defined object. And of course, if the space of observables over which it is defined is large enough, then it will give us a very decent representation of the dynamical system as a whole. And on top of this, we have all these nice properties that it is a linearization, so we can do spectral decomposition, and we can use it for interpretability, but also control. So I'm not into control too much. So, but of course, if you have a linear dynamical system, then we have tools to do control over it. The approach is the same that Massimiliano described just before me. So instead of approximating the transfer operator over the full set of observables here, so we assume that the transfer operator, that the dynamical system is ergodic. So we have a unique invariant distribution, which is pi. And within this assumption, we know that the transfer operator is well defined on the space of square integrable functions with respect to this distribution. But of course, we only have, so we assume only to have samples from it. So in a way, we don't even know what is the invariant distribution because we have samples. We just know that it is well defined over this space. And so we choose a subspace, and pretty general reproducing Cantilever spaces are a good tool to define these spaces of hypotheses. And really the nice thing about reproducing Cantilever space is that every function within it are linearly parameterized. So we need to define a feature map phi, and then automatically, as soon as we define the feature map, we have a space of observable, we have an hypothesis space. So in this talk, I will speak about how do we learn a good H from data. And this will really mean how do we learn a good phi. And that's why it's representational learning, because phi is just an embedding of the data. Okay, so this is the learning setting. When I say this learning setting, I would say that two learning problems arise. So the first one is the one that of the previous talk. So assuming that somebody gave us a good hypothesis space, then we would like to learn a linear estimator out of it, defined on H. But the problem is that in reality, it is very difficult that we know what is the perfect space. So for example, in the talks by Igor, he said, a good embedding is when we know the eigenfunctions. We know that the eigenfunctions allow us to construct good hypothesis space. We might not know what are the eigenfunctions in a way. If we knew that, we would know already a lot about the transfer operator itself. So when no off-the-shelf, and really off-the-shelf means, say, kernel methods, standard kernels like the Gaussian kernel, do the job, then we can try to learn it as well from data. And this is important, and I will show you a couple of examples in this case. For example, when we deal with structured data. So if you imagine we have a graph which evolves over time, and this is a really important case because when you model the dynamics of atomic systems or proteins, this is really graphs evolving over time. Same with images. And so basically the problem one is the operator regression. So we have already a good representation, a good hypothesis space. We would like to learn a linear operator. The problem two is to learn the representation. So to go from the data to project up to a good embedding of it. Nice, how do we do that? Well, and this really comes back to the stochastic dynamical system. We use statistical learning settings. So we leverage the same decomposition of the error that Massimiliano showed before. So we know that whenever we would like to learn a transfer operator, or more specifically, its restriction to the hypothesis space, then we can bound the distance between what we learn from data, the hat here stands really for the fact that we learn it from data, to the true target. And okay, we have this decomposition. I will be concerned about this. This is a representation error because if you see, it depends on the choice of H, but it doesn't depend explicitly on which kind of estimator we choose. And which kind of estimator here, I mean, say, kernel ridge regression versus principal component regression or whatever other method. So this depends only on the hypothesis space, and then this depends on the algorithm if you want. Okay, so the idea here is that we would like to define an approach which, starting from data, constructs an estimator or gives us a procedure to minimize the representation error, essentially. I will not go over the full proof, but I will try to give you an idea now. The first bit of information that we need is that the representation error can be upper bounded and lower bounded by these two terms, where the new piece that we have here is the covariance matrix, or covariance operator in general, because this is an abstract Hilbert space. The nice thing about this bound is that you see that both the lower bound and the upper bound depend on this term, and this is going to be the main subject for later slides. But whenever we have that the covariance operator, so whenever we choose an hypothesis space for which the covariance operator is equal to the identity, then the upper and the lower bound match. So this will give us already a piece of information that we would like to have an hypothesis space in which the covariance is close to be the identity. And this is related to also the metric distortion issue that basically destroys or degrades the prediction of the spectral functions, as we showed in the spectral rates paper. So the idea is that, okay, first we would like to have a hypothesis space for which the covariance is close to be the identity, but not only, because we also have this other term. And this is a bit more tricky, but the general idea is that we will use classical results, which is the Eckart-Young-Mirsky theorem, on this object here. And the Eckart-Young-Mirsky, it tells us that the best finite rank approximation to a matrix, but also can be extended to operator, is essentially the singular value decomposition of it. And using this idea, we have a way to minimize the representation error. So I will fast forward a couple of lemmas. So there are mostly computations. If you want, I can discuss them more in detail. But long story short, we can define a functional p of phi. I explicitly written down the dependence on phi because what I would like to point out is that all of this can be computed just by putting, say, phi to be equal a neural network and then optimize over the parameters of the neural network. So if we parameterize phi in some way and then we do gradient descent out of it on this score function, we have a way to minimize the representation error. And the object that you see there are just the covariance matrices. Okay, so those are the expected value of the outer product of our feature map. Nice thing about writing everything in terms of expectation values is that whenever we have data, we can just replace the expectation values with the empirical expectation. So sum over the data points, and 1 over n, where n is the number of data points, sum over the data points. And R, up there, is a regularization term encouraging that the covariance matrix is close to the identity, as I discussed in the previous slide. Okay, couple of comments. Pi is a function of the feature map. P is a function of the feature map. I already said that. And of course, whenever we optimize over phi, immediately we are learning an hypothesis space H, because H is just essentially the span of the feature map over all the points in our domain on our state space. Problem with this, so this is perfectly well defined, but not very practical. Why it's not practical? Because the usual algorithm is that as I've anticipated, we parameterize phi with a neural network. We compute the covariances, we compute the norms and the regularization, all good. And then we do backpropagation, so we take the gradient with respect to the parameters of phi and do gradient descent. But the problem is that, as you can see, there are the pseudo-inverses of the covariance matrices. And if you try to backpropagate through pseudo-inverses, good luck, meaning can be done, but we have, so there are very well-known results showing that it is highly unstable. And then what we've done is also to propose a relaxation of this core function. And this is much better because we replace the pseudo-inverses just with the inverses. Of course, we lose information in a way here because we don't project it. So the pseudo-inverses here are really needed to adjust the metric deformation induced by the choice of H. And here we are relaxing this assumption. But we have a theorem showing that whenever, so that the global optimum of the both coincides. So if we happen to be in the global optimum of S, then we are also in the global optimum of P, and then we're happy because we minimize the representation error. So there is really, so if we are in a regime in which doing backpropagation on P is feasible, we're happy, we do that, we usually converge faster. If it's not possible, as usually in large-scale systems, and I will comment about it in a second, then this comes to the rescue. It's a bit slower to converge, meaning that we really need more iterations, but it works. It's a bit more stable. Okay, enough math. I will speak about a couple of examples. So in the first one, we created an artificial dynamical system starting from the MNIST dataset. And what we've done is that we sample the digits in order. So the dynamical system was consisting in sampling the digits of a 1 and then sampling the digits of a 2 and so on, modulus in this case 5, but we can do for every digit. So whenever we reached 4, the digits 4, then we sampled back another digit of 0. And those are our training data essentially. And what we've done is to compare different methods. So linear stands for really doing DMD and trying to use DMD to forecast. So starting from a seed image, which is coming from the test set, using the model that we have, the model of the transfer operator that we fitted to forecast the future digits. And you see that if you use the linear model, the DMD, well, it doesn't do super well because those are images, and then who knows what kind of linear relationship can allow us to forecast a next image. Then we have all that you can see are, so this is the dynamical autoencoder, is very famous work by Stephen Branton, I think 2017. This is consistent autoencoder, which is a modification of this approach. Then we have VampNets, which is another representation learning scheme originated from the field of molecular dynamics. But long story short, you see that our two approaches, DPNets, which is ours, stands for deep projection nets, because the object that we optimize over are related to projection operators. And the relaxed version, starting from a seed and then using multi-step forecasting with these models, we do, we are able to reconstruct images which are readable. So this is really learn the representation of this data set. And most importantly is that this is fully unsupervised. So as I said, the training data are just images. We never provide the algorithms with the true labels. So in a way, the representation that we learned understood that there is a structure in each number and correctly parameterized it. And then if we use the, if we take the first two eigenfunction and we use them as a dimensionality reduction, we see that, for example, the linear is not able to distinguish across the different digits, but our methods, and most importantly the DPNet, so the unrelaxed one, really, if you project on the first two, on the space spanned by the first two eigenfunctions. Within this representation, we really can cluster the digits. So we learn the structure within the data. Okay, but this is a toy example. Let's go to the real stuff. The real stuff is studying molecular dynamics. I'm actually a physicist. We studied the dynamics of this protein, which is 166 atoms. And there were more than 500,000 samples, so snapshots of this protein in the data set that we studied. And the idea here is that whenever we learn a meaningful representation, a meaningful hypothesis space, then we are able to extract physical information which are closer to the reality, and the model is more effective. And then, for example, in the case of molecular dynamics, it is known that the leading eigenfunctions of the transfer operator are very important because they describe the chemical events which occur on longer timescales. In the case of proteins, for example, it can be changes in the conformation which allow for a drug to bind with the protein. So these kind of results are extremely important in, say, drug design. And what we've done is, so we also have reference values from these simulations, so reference values from the actual physics, and then we train different models. So the DPNet is ours, and by the way, this is DPNet relaxed, so the one which substituted the pseudo-inverses with inverses, because every other methods failed to converge. So not only the DPNets, but also the VAMPNets, which was proposed again in the, because this is a very large scale example. And then we use the Nystrom approximation of PCR and RRR. And as you can see, we recovered the physical properties that we had, still very far from being close to the reference, but much better. And this is also very similar to the previous slides, the projection over the first two leading eigenfunctions that we fitted. And you can see that with the DPNets, we can resolve much more structure. And long story short, whenever you see a minima here, it tells you that there is a state in which the protein really wants to be there. And you can see that here we resolve 1, 2, 3, 4 states in this region, while with a worse representation, we only are able to resolve a single state without having much more information on the physics. Okay, that was it. This is part of a series of work on dynamical systems. I would like to acknowledge mostly also Vladimir, which is a co-author, and it is on all of this paper. We also have a code to implement a lot of these algorithms and many others collaboration. Thanks a lot.